Before starting isolated and non-isolated singularities, first of all, let us discuss what is the zero of the function and what is the order of the zero of the function. Zero of the function. Zero of the function is nothing. It is a particular value. When we substitute that value in our function and our function becomes equal to zero, then that particular value is said to be zero of the function. For example, let f of z be any function like here, f of z is sine z, and when I put z equal to 0, means sine z equal to 0, and we all know that sine z equal to 0 at sine n pi. Therefore, for all n belongs to z, that is set of integers, all these are the simple zeros of my function f of z. Then after zero of the function, next is order of the zero. What is the order of the zero? For calculating the order of the zero, we have to find the derivative of our function. Let f of z be my function and a be the zero of that function. Then we calculate f dash z, f double dash z, and so on. And when I put this z equal to a in my function, that is f of a, and calculate the value of f of a, and it comes out to be zero. Similarly, when I put z equal to a in my first derivative, and it again become equal to 0, and in the similar way when I put z equal to a in my m minus 1th derivative, and it again become equal to 0. But when I put z equal to a in my mth derivative and it comes out to be non-zero, then this z equal to a is said to be 0 of my function f of z of order m. For example, like here f of z is z minus 1 whole square. When I calculate its first derivatives come out to be 2z minus 2. Okay? And when we put z equal to 1, my f of z become equal to 0, my first derivative become equal to 0. But when I calculate f double dash z and put z equal to 1, then f double dash 1 does not equal to 0, it comes out to be 2. Okay? Then this z equal to 1 is said to be 0 of f of z of order 2. Okay. After calculating zeros and order of zero, let's discuss what are regular points and what are the singular points. Regular points are nothing, but these are the points at which my function becomes equal to analytic. Okay. That is, a point z equal to a is called regular point of f of z if f of z is analytic at z equal to a. For example, our exponential functions we know e raised to power z can be expanded like 1 plus z plus z squared by 2 and so on. And for every value of z, my function is analytic in my domain, that is in the domain of complex numbers. So z equal to a is said to be regular point of function f of z. There is very important result, that is f of z is entire function, then every complex number is regular point for my function. Similarly, singular points. Singular points are those points at which singular points are those points at which my function ceases to be analytic. That is, it is that point at which my function does not equal to analytic. For example, if f of z is 1 by z and then put z equal to 0, my function f of z becomes equal to infinite. This function does not exist at z equal to 0. Therefore, this point z equal to 0 is said to be singular point for my function. After discussing regular points, singular points, let's move toward our main topic, that is isolated singularity and non-isolated singularities. Students, singularities are of two types. One are isolated singularities and other one are non-isolated singularities. Isolated singularities are further subdivided into removable singularities, poles, and essential singularities, and we will discuss these one by one. Before discussing removable singularities, poles, and essential singularities, first of all, let's discuss isolated singularities and non-isolated singularities. First of all, isolated singularities. Any point z equal to a is said to be isolated singularity of a function f of z if it satisfies these two conditions, that is, f of z is not analytic at z equal to a, but my function f of z is analytic in the deleted neighborhood of z equal to a. That is, there exists a neighborhood of point z equal to a that contains some other singularity of my function. For example, if f of z is 1 by z, when I put z equal to 0, this function z minus 1, z minus 2, z minus 3. As we see that this function ceases to be analytic at z equal to 1, z equal to 2 and z equal to 3. Because if I put z equal to 1, this function becomes infinite. When we put z equal to 2, it again becomes infinite. And when we put z equal to 3, this function again becomes equal to infinite. Therefore, these z equal to 1, 2 and 3, these are the isolated similarity of this function because this function is analytic everywhere except these 3 points. Similarly, let's discuss one more example. If f of z is 1 upon sine pi z, and we know that this function ceases to be analytic at z equal to n pi, that is n0 plus minus 1 plus minus 2 and so on. But it is analytic on all other points, therefore these points are isolated similarities for this function. Okay, there is very important result, that is limit point of zeros of a function is always isolated similarity. Let's discuss this concept with the help of an example. For example, if f of z equal to sin z minus 4z, and we all know that zeros are always calculated by putting the numerator equal to 0, then I put f of z equal to sin z minus 4z equal to 0. This gives me tangent z equal to 1, and I know tangent z equal to 1 at n pi plus pi, when z equal to n pi plus pi by 4. Now, when we put n from 1 to infinity, z becomes infinite at n equal to infinity. Therefore, this is the limit point for this function. Z equal to infinity, this is the limit point, and this limit point is calculated from where? This is calculated from the zeros of my function, and we know that limit point of the zeros of the function is always isolated similarity. Therefore, z equal to infinity is isolated essential similarity for my function. Okay. Now, move to our non-isolated similarities. A point z naught is called non-isolated similarity of f of z if every related neighborhood of z naught contains at least one similarity of f of z. Okay, if there exists at least one similarity of f of z in its deleted neighborhood, then z naught is said to be non-isolated similarity. And there is again very important result, that is limit point of all of any function is always non-isolated essential similarity. For example, I consider this function f of z is equal to 1 upon sine pi upon z. This is this is sine pi upon z. This is not 2. This is sine pi upon z. Okay. For calculating the pole, we always substitute denominator equal to 0. When I put sine pi upon z equal to 0, it gives me value pi upon z equal to n pi, and from here z equal to 1 upon n. Okay. And this n takes any value from 0 to infinity. When this n equal to infinity, z comes out to be 0. Therefore, z equal to 0 is non-isolated essential similarity because this value is calculated from pole, and we know that limit point of the pole is always non-isolated essential similarity. Okay. One more example to understand this concept. Let f of z is equal to tangent z, and we want to find the value that at z equal to infinity we have isolated similarity or non-isolated similarity. Let's discuss this question. F of z is tangent of z, and we have to check this value z equal to infinity. Okay. When, whenever we have to check any value at infinity, we preferably change it to 1 by z so that we can check that value at 0, which is more easy for us. So instead of calculating f of z, we calculate f1 upon z. Okay. That is tangent 1 upon z. And when f of z, then z upon z equal to infinity. When we calculate f of 1 upon z, then we take the value z equal to 0. Now, isolated singularity for this function. But students, when this n is very much large, it is 1 crore or more than that, for 1 crore or 1 crore 1 or 1 crore 2, for all these values are infinite. We can consider this infinite. This z, these all are very nearer to z comes out to very nearer to 0. It means there are infinite number of singularities in the vicinity of z equal to 0. Okay, so all these are, for this reason z equal to 0 is said to be non-isolated singularity for this function. There is very slight difference, but to understand the concept, when we take this and different, nearly equal to infinity, merely varying values in points. In that case, we have infinite number of similarity in the vicinity of z equal to 0. And all those similarities, for that reason, z equal to 0 is said to be non-isolated association similarity. Okay? There are, but another method to understand the concept of singularities. For understanding that concept, we must know the Lorentz series. You know that Lorentz series is expanded like this: f of z equal to this switch n from 0 to infinity a n z minus a raised to power n plus n from 1 to infinity p n z minus a raised to power minus n. Student, the second part is called principal part, which is with negative power, and this is of very much more importance for calculating the singularities, concept of singularities. From this Lorentz singularity, we can easily discuss our removable singularities poles. For removable singularities, if the principal part of f of z contains no term, means the term with negative powers are absent in any series, it means that function must have a removable singularity. And one another definition to explain the concept of removable singularity, that is, if we calculate the value of f of z at z equal to a, and this value exists finitely, then z equal to a is called our removable singularity. For 4, if the principal part contains finite number of terms, then that function is said to have a pole. For example, this function f of z is equal to sin z upon z cube. I expand sin z like this, and from here I found two values of z in negative power, that is z square, and here I can write z raised to power 0. Okay, for this reason z equal to 0 is said to be pole of minus function of order 2. One more another definition to define pole. We define f of z equal to phi of z upon z minus a raised to power n. This z minus a is nothing but it is that point at which we want to calculate our pole. Okay, in this way we can also calculate our pole. For example, if f of z is equal to 1 upon z square, but we do I have to calculate the pole at z equal to 0. Okay, I write it z minus 0 whole square. It doesn't disturb my function, limit z approaches to 0, and I found this is equal to 1, that is a finite value. Okay, therefore z equal to 0 is said to be pole of order 2, because here r is 2. In this way we can also calculate the pole of my function. One more example to calculate the pole of the function. In this there is a function f of z equal to 1 upon z square minus 3z plus 2. Factorize this factor. After factorizing z square minus 3z plus 2, factors are z minus 1, z minus 2. Means for calculating the pole, I put the denominator equal to 0, and from here I found two values, z equal to 1 and z equal to 2. And this z equal to 1 and z equal to 2 are said to be simple pole of my function. Students, if in some question I got some z minus 1 whole square, z minus 2 power 3, in that case I said that z equal to 1 is the pole of order 2, z minus z equal to 2 is the pole of order 3. In this way we can calculate the poles of any function. And last one is essential similarities. Okay? If the principal part of the Lorentz series contains infinite number of terms, in that case z equal to a is said to be have essential singularity. Okay? And one another definition to define essential singularity, a point z equal to a is called essential singularity of function f of a, that if we calculate the limit of our function and that limit does not exist, then we said that that point is essential singularity of my function. Let's discuss this concept with the help of example. Like f of z is equal to sine 1 upon z. I expand my sine function. Here, in the principal part, we have infinite numbers, because we know that this series run like this up to infinity 1 upon z, here power is 3, here power is 5, then next power must be equal to 7, and like so on up to infinity. If we have infinite number of terms with negative power, principal part contains infinite number of terms, therefore z equal to 0 is said to be essential singularity of my function. This is all about